Hello everybody, welcome to Puzzle Buster, Java Challenges Solved. Boy, have I got a challenge for you. The name of today's challenge is Fibonacci. The object of the challenge is write a method that returns the nth digit in the Fibonacci sequence. Now, those of you who are math geeks like me are well aware of a series of numbers called the Fibonacci sequence, and if you're not, the Fibonacci sequence is simply a series of numbers where every number in the series is equal to adding together the previous two numbers. And as a demonstration, if I jump into Eclipse, I can show you very briefly. This Fibonacci sequence looks something like 1, 1, 2, 3, 5, 8, 13, so on and so forth, where every number is simply an addition of the previous two numbers. 13 is 5 and 8, 8 would be 3 and 5, 5 would be 2 and 3, so on and so forth. And this is a fun series of numbers that tends to crop up everywhere in nature. It's the source of something called the golden ratio, which is in turn the source of something called the golden spiral. Now, it's kind of a fun series of numbers, but what's even funner is using recursion to solve this problem. So if you'd like to take a moment, pause the video, and think through how you might solve this yourself. Otherwise, let's solve this together. And so the nature of all recursive methods is we need to have a base case. We need to have a case in which once the method is called for some final time, it uses the base case to stop the recursive calling. Without the base case, the method would continue to call itself recursively until the computer ran out of memory, and so that wouldn't be any good. And so now we can approach this in the most intuitive way. As we know that the first two digits in the Fibonacci sequence are equal to the number 1, we know that if n, which is the nth digit, the nth location, is being passed through, if it's equal to either 1 or 2, we're simply going to return a 1, and we can use that as the base case to terminate the recursive loop. And so let's write a public static. We're going to return a long, and we're going to call it fib, and we'll have an integer called n. N is going to represent the location in the series that we want to return. And up here you see I had a main method with some print line statements to the console already written out. And I'm going to be calling the fib of the location of the third digit, the fourth, fifth, sixth, seventh, and then finally the 50th digit. And what I expect it to return is, of course, as we saw in the sequence, 2, 3, 5, 8, 13, and then by the 50th digit, it's going to be some incredibly long number right here. So now let's see if we can use recursion to make this work. So first we're going to write our base case. We're going to check to see if n is less than or equal to 2. And if it is, we're simply going to return 1, thus breaking the recursive loop. Now if it's not, what we need to do is we need to return, and then this is where recursion kicks in, a call to the same method, which would be fib, passing through n minus 1, and adding that to another call to the same method, passing in n minus 2. And this represents the previous two numbers being added together. So you can see that this is sort of like an intuitive solution to this. We'll see if this works, and what we'll expect to get down here in the console is going to be this series of numbers right here, the 2, 3, 5, 8, 13, and then this number as well. So let's see if we got this right. So if we run this, we see we have the 2, 3, 5, 8, 13. However, we have not got this number here, and we can see that the program is still running. And so what's going on here? Well, as it turns out, every time it has to call itself recursively, it has to do so in what's called n to the second, or n squared time. And so for every increment of n, it's going to be exponentially longer. It's going to have exponentially more calls to itself. And so it actually is still running. It's trying to loop through this many number of times to get to this number. And there it is, finally propped up right there. And so what is exactly going on here is that because it's the exponential, because the method is of an exponential time complexity, as n increases, it becomes exponentially more computer intensive to run. And so while this is a very intuitive way to solve the Fibonacci sequence, it's not a very processor friendly way. And so what's a different way that we could approach this that would return the same number but much quicker? Well, as it turns out, if you were to draw a tree of the Fibonacci sequence, you'd see that there's many repeating digits. And so even though it's figuring out that the addition of, for the nth position of 3, it's an addition of 2 and 1, it's actually having to figure that out very many times over for all 50 calls to the method. So let's see if there's a different way we can write this that'll be a little bit quicker, a little bit more processor friendly. And so We'll go ahead and delete this method. I'm going to clear the console out so that we can see if we can make this any quicker. And so what I'm going to do instead is I'm going to make a couple of imports. We're going to use a hash map. And so I'm going to import from java.util a hash map. And I'm also going to import from java.util a map. Now the hash map and the map are going to allow us to build a data structure, and in this data structure we're going to, every time we make a call, if the map doesn't already have a recording of that nth digit, we're going to go ahead and put it into an array. We're going to store it into an array so that we can later search that array to see if there's an occurrence of that, and simply pull it from the array rather than have it sequence all the way out to figure that number out over and over and over again. So something like that is going to look like, we'll do a let's come up here and define a variable. We're going to make a static map that we're going to have as linking an integer, which is going to be the location of our digit, and then a long, which is going to be the value of the digit. We'll call this memo, and we'll set it equal to a new hash map, like so. And once we have that, let's go ahead and write this method one more time. This could look like public static, we'll do a long, and it's going to be accepting an integer called n. All right, let's get to work here. And so what we need to do is we need to, of course, check the base case again. So let's do, if our memo does not contain the key n, then let's go ahead and perform the check to see if n is less than or equal to 2. In which case it is, let's go ahead and put into the memo the value of n, and then the value we know that it should be, which is going to be 1. Else, let's put into the memo the value of n plus another call to the method, which will be fib n minus 1 plus fib n minus 2. Now the beauty of this is that it's only going to have to call this recursively one time. And once it calls it recursively, as it's storing it into this this map, the next time that it ends up going through that second or third or nth recursive call, it's going to simply find it in the map and it's going to call it from there. And so it won't actually have to go through the entire tree of recursion. So let's see here. Now, after this if statement, we're going to go ahead and assume that it's in the memo, and we're going to return whatever the memo is of n, like so. And as you can see here, I'm getting an error with the put, and that's because I have to cast this to a long. And so let me put an L after that so that I can signify that that's going to be a long. And this looks like it should be right. Let's see if we can run this and get that last final number any quicker. All right, so as you can see, that was lickety-split. We were able to get not only the first 5 digits, but that final digit almost instantly. And again, it's due to the nature of the fact that rather than having to go through the recursion over and over and over again for numbers that it's already figured out, it's storing those numbers to a map, checking the map to see if that number has already been stored, and then simply calling that from the map rather than having to go through the entire recursion. And so much quicker and much more processor-friendly way of solving this, and it's called memoization. It's a form of dynamic programming, as well as recursive programming. And so hopefully this video has been fun and entertaining. Look forward to seeing everyone back in the next one. Thank you so much and have a wonderful day.